Okay, let's get started. So we were speaking last time about the supernorm problem. We had F, a holomorphic modular form. Of weight k. And level n, which is cuspidal, and it's a Hacke eigenform. And we were interested in how large is the sup over tau in the upper half plane, f of tau, imaginary part of tau to the k over 2. With some kind of normalization. And we normalize this so the average size is 1. So like the integral over upper half plane, or the average of f of tau squared m tau to the k is 1. And then the conjectural answer is it should be n to the epsilon. So like O of n to the epsilon for all epsilon. So it should be growing like only a very small power of n, as kind of n is going to infinity. For k fixed. Oh, and I should say n. Let me also assume n is square free for simplicity.
This is for the type of phones you talked before, like gamma 0 n phones.
Yeah. So for this conjecture, gamma 0 n versus gamma 1 n doesn't matter. The results I'm going to state. Well, okay. It's for gamma 0 of n. Technically, it works for gamma 1 of n for some characters, and that's not a fundamental limitation. It's just it was a little bit simpler to put in that restriction. So yeah, let's just assume everything is gamma 0 n. A lot of the results I'm speaking about also generalize to gamma 1 of n.
Excuse me, should be that conjecture because presumably small z any power should be some power of logarithm, yeah? Do people have some feeling?
I don't know what people. I don't know what people believe as to the exact value here. I mean, you should say that, okay, so the most optimistic thing you could say is you should say this wave, this eigenfunction should behave like a Gaussian locally. Its value at a point is Gaussian with mean 0 and variance 1. So the probability that it's bigger than a constant times root log n should be like a power of n. And so probably there's going to be nowhere in the modular curve where it's bigger than a constant times root log n. So you could say maybe the correct thing is of size like comparable to root log n. That would be very, very, very ambitious. There's lots of reasons you might worry modular forms don't behave exactly like a Gaussian in that kind of in their very extreme values on very large scales. I don't know what people have conjectured in terms of precise estimates, but in any case, all the theorems are pretty far away from this.
Another way to normalize eigenfunctions using the Q expansion that you
Correct.
normalize so the coefficients gives you the eigenvalue.
Yes, and right, and then there's like an n to the epsilon of difference between those two normalizations. There's an n to the epsilon of difference between those two normalizations. And maybe that difference is also, you can really reduce it to a powerful log n if you're careful. But in this subject, people tend to just not worry about n to the epsilon factors and focus on improving the exponent.
So the proof that those normalizations differ by n to the epsilon is easier than what you're trying to. Yes,
I mean it's a theorem of Rankin and Selberg. I think it's proven using the Rankin-Selberg method at least. You can if you integrate this abs value squared for a form which is normalized by the Q expansion with leading coefficient Q, then you'll get basically the L function, the symmetric square L function of the form evaluated at 1. And so then you can estimate the value of the symmetric square L function at 1 by kind of standard L function techniques. Yeah, so it's much. In fact, the theorem that I'm stating is really proved using the Q expansion normalization, and I just use that argument. So that argument is literally a subset of the argument of what I did. And so the easiest bound you can kind of do, which is not quite trivial in this setting, but it's not super hard, is O of n to the 1/2 plus epsilon. Basically, if the form is large at some point, it's got to also be large at nearby points by like general properties of holomorphic functions. And given that the size of the modular curve it has area of roughly n in the hyperbolic metric, you get this n to the 1/2 plus epsilon bound out of that.
About passing from new forms to old forms, this doesn't change anything.
No, it does. So the thing is, when you have an old form, these should be new forms. When you have an old form, you have choice. You have two different ways to bring the modular form from a small, and then for the sup norm, choice is scary because if you have a lot of choices, let's say it's an old form at many primes, then you can choose exactly the linear combination of those choices that maximizes the value at one particular point.
So it could be false for old if you allow old forms.
Yeah. But if you specify a way of choosing, if you specify a particular rule, then you kind of get a new problem. Every way of choosing like a local vector gives you kind of a new variant of the supernorm problem. And that the new form seems like a pretty natural vector to choose, but it's not the only natural choice. And then there's a series of works in analytic number theory improving this bound, improving this exponent. And it got stuck for a while after the work of Harkosh and Templier, who was n to the 1/3 plus epsilon. And so I then did something in a function field analog by a geometric method. So by myself, in an FQ adjoint T analog. Well, the right way to say it is O of n to the 1/4 plus delta, where delta goes to 0 as Q goes to infinity. So for each Q, the exponent is bigger than n to the 1/4, but as Q grows, the exponent gets closer and closer to n to the 1/4. And so this is a case where by the geometric method, I was able to improve on what was achieved by purely analytic methods, but not, like in some of these other problems, not an incredibly dramatic improvement that's completely different from what is achievable analytically. It's just kind of an improvement of the exponent. And even worse is after my paper, Cayutin and Nelson and Steiner got O of n to the 1/4 plus epsilon, where epsilon is going to 0 as n goes to infinity, which is stronger, because if you, I mean, they didn't do it in the FQT setting, but if you did it in the FQT setting, this would go to 0 for fixed q, and not just as q goes to infinity. So my geometric method is kind of superseded in the implementation that I wrote. But the reason that I'm still bringing this up, and I still think it's interesting, is there's a general method and a general approach which I only did kind of one version of, and there's probably better versions of it and more general versions that work on different problems where the analytic methods are harder. So I think in the future this geometric method will probably be able to prove stronger bounds. But I wanted to put it in context first. So what is in the FQ joint T analog, F is a new form on GL2 FQ of T, which means it's a function from some adelic double coset space, you can say. GL2 FQ of T modulo gamma 0 of n to C. And another way of saying that is it's a function from the 2 points of the moduli space Bun 2 n FQ to C, where this parameterizes rank 2 vector bundles on P1 with a subline bundle. Over the divisor n.
Can you, when you discuss those results, do you choose a rational function field FQT just for simplicity? That is, do you do it also for algebraic curves over FQ, or do the methods are limited to?
So most of the arguments in my paper work for algebraic curves. I don't know most. A lot of arguments in my paper work for algebraic curves. However, there is one crucial calculation which I only did in the case of P1. So for that reason, I'm going to stick to P1 and I'll explain why that is. So this is one example of the kind of thing where I have a general approach and I did a first proof of concept, but I think that further results will be proven by the approach in the future, by me or by someone else.
Before going on, one can ask a kind of intermediate question, because it's kind of subform is like L infinity. We consider integral, I don't know, 6 powers of square or whatever, kind of, and that could be like LP norms.
Yeah, so
more manageable, I think, from because you integrate integrals, functionals will be kind of homological interpretation of this, I suppose.
Yeah, I don't. So I don't know how directly more manageable it is. So it is true that the method I'm going to describe gets a bound for the LP norm, which is not just what you get by combining the L infinity and L2 bounds. And the reason for this is the method gives you a bound for the value at each point by some explicit function of that point. And so you get the supernorm bound by taking the sup of that explicit function, but you could also take higher intervals of higher powers of explicit function. So you're right that these LP norms for even integer p have a geometric description as some explicit cohomology group, but I don't know how to compute anything about that cohomology group for p greater than 2. So it is some cohomology group, but I don't see how it is a cohomology group that we can really get our hands on and prove some like nice cohomology vanishing result for. But yeah, so the p norm is absolutely like a valid question. So, well, I mean, in fact, as we're kind of gesturing at there, so the crucial theorem we'll use is the theorem of Drinfeld, which is that f is up to constant the trace function I'll explain that after I write it, of a perverse sheaf on bun 2. N. So I put the script because I'm combining here two different theorems of Drinfeld, because he didn't prove this construction of perverse sheaves on bun 2n with the goal of understanding something about automorphic forms. He proved it with the goal of proving the Langlands correspondence, of constructing the automorphic form from the Galois representation. So the theorem inputs a Galois representation and outputs a perverse sheaf, and then it uses that perverse sheaf to find the automorphic form corresponding to the Galois representation. So that means that if you want to apply it to an automorphic form, you have to use the automorphic to Galois direction of the Langlands correspondence, which is a different theorem of Drinfeld. So this is actually using both directions of the Langlands correspondence, and the squared is just a little joke about that. So the point of this is, so this gives me a cohomological interpretation of the value at a given point. It's from the stock cohomology of this perverse sheaf. So maybe I'll write, I should maybe, okay, let me write pure here. It's like going to be a pure perverse sheaf of some weight depending on the constant. And so the key thing is f of x is equal to sum I trace of prob q on the stock of this perverse sheaf, the ith cohomology sheaf of this perverse sheaf at the point x. So we have a bound for the Frobenius eigenvalues on here, which come from the purity, which is kind of clear from the construction of the sheaf. So we need to bound the dimensions of the stock, dim hi of this perverse sheaf x. So for k this sheaf, for k the Hecke eigensheaf, because the sheaf constructed by Drinfeld. So this puts the question in the kind of general context. If I have a perverse sheaf on a variety, how do I bound the dimension of its stalk at a particular point? And there is a theorem of David Massey that gives an answer to this question. Proved a bound on dim hi okay stalk at x for an arbitrary perverse sheaf k on a variety y in terms of the characteristic cycle. So Massey gives us a bound if we can calculate this invariant called the characteristic cycle. What is this? So the characteristic cycle of K is a cycle on the cotangent bundle of the variety Y of dimension dim Y that is conical or scale invariant. So to every perverse sheaf, is associated algebraic cycle in the cotangent bundle of the variety. And so this is some kind of version of like microlocal analysis for sheaves. Well, in fact, there exists a cycle for an arbitrary complex of constructible sheaves, but for perverse sheaves, it's an effective cycle, which is nice. This cycle has an explicit construction for D module. So if you use the Riemann-Hilbert correspondence and your perverse sheaf corresponds to a D module, there's an explicit thing you can do for the algebra of D modules to recover the cycle. This is, yes, this is in characteristic 0. Well, yes, the D module story is in characteristic 0. Massey's rule is in characteristic 0. So, yeah, so. Yes, okay, if you remember, although I'm sure you could also have figured it out. Yes, this is in characteristic 0. And so to apply this to characteristic P, we need to first prove a characteristic P analog. Well, I haven't said what the result is in characteristic 0, so I'll say that. But yeah, so then I prove the characteristic P analog of it using the characteristic P characteristic cycle theory developed by Takeshi Saito. So let me say what one line about what the characteristic cycle of K is doing. So CCK measures the vanishing cycles of K. So if you look at F a map from K to A1, then, oh, sorry, yeah, X state. It's actually Y, I thing. Yeah, y to a1. Then our phi of k is supported on like the intersection of the characteristic cycle of k with the derivative of f and the intersection number controls the amount of vanishing cycles.
So in fact, you have only the middle degree if you are doing it transversely, the middle degree.
Yeah, yeah. If the intersection is finite, I think you'll only have vanishing cycles in the middle of degree. And the intersection number controls in characteristic 0 the dimension of the space of vanishing cycles at this point. In characteristic p, it would be the dimension plus a Sawin conductor, because everything is more complicated in characteristic p. And so the formula, the bound that Massey gives is in terms of what's called the polar multiplicities, which are a generalization of the usual notion of multiplicity. So what is a multiplicity? Like the multiplicity of a cycle Z on a variety y at a point x.
Your cycle cotangent bundle.
So I'm going to first give the definition for an ordinary cycle, and then I'll give the definition for a cycle in the cotangent bundle. Is the local intersection number at x of Z with a general smooth subvariety W of dimension dim y minus dim z through x. So you take your cycle and you take your point, and then you choose the most general thing you can fit through this point. So you take a smooth variety of complementary dimension through that point, and you let them intersect, and you want to attach some number to the intersection, so you kind of wiggle both of the cycles, and you calculate the total number of intersection points, which is near to that original intersection at x. And so this is like the natural thing you can do to input a cycle and get a number out of a point, is you intersect with some very general cycle going through that point. And so like the polar multiplicities are applying the same concept to now a cycle in the cotangent bundle of y, and we're going to get a number from the local behavior, not just at a point, but in the entire cotangent space over that point. So for C, a conical cycle on cotangent bundle of y, I want to take P of C, the corresponding cycle on P of T star y. So when I'm projectivizing this vector bundle, I want to remove the 0 section and mod it by scaling. So you get a projective bundle of dimension 1 less. And P of C, I'm going to mod out C by scaling, so it becomes a cycle of dimension 1 less. And the ith polar multiplicity of C at x is the local intersection with a general I-dimensional projective subbundle of P of T star y on a general smooth subvariety of y through x, and the smooth subvariety has codimension I. So in this kind of just in y, the only thing I could take through the point is I could take a smooth subvariety, and I need to take it to the complementary dimension. Here I can do something more complicated very naturally. I can take a smooth subvariety through x, and on top of that smooth subvariety, I can choose a subbundle of this projectivized cotangent bundle, a smoothly varying system of projective subspaces. And I want to choose them so that the total dimension is complementary, so that I have a bunch of choices of how to do this. And then I take one of those, and I look at like the local intersection number in the fiber over x. So in other words, I wiggle it and I wiggle C, and I look at how many intersection points live near the fiber over the point x.
Okay. It would be more natural to consider this I-dimensional subbundle to contain perturbation of conormal bundle, yeah? Because we have natural conormal bundle that is.
Yeah, so I think that the conormal bundle I think the conormal bundle probably does give you enough genericity here.
One less dimension, so.
Oh, you're saying it's the wrong.
Yeah, no. Just conormal bundle gives you again n-1 dimensional thinking factorization.
Okay, because you want the intersection to be. You want to expect the dimension of the intersection to be 0.
Yeah.
So of course to be, and so this means that on the T star y it should be 1. You expect intersection of dimension 1. So if you intersect two things of half the dimension, you expect it. So you should.
Yeah, it should.
This means that it takes 1 dimension more than the conormal bundle apparently, because it takes I-dimensional in the sense of projective space. And other finds, so it's kind of.
Yeah, but to reflect geometry, it's natural to take containing this conormal bundle. Yeah, not general projective bundle. It's kind of used. But maybe it's just the same because it's.
But you could take one which contains the conormal bundle, and of course in characteristic 0, the conical cycles that we have are much more limited. They are just so but maybe in characteristic P you need to do.
Maybe. Because it's not Lagrangian, it's a characteristic P.
So yeah, I mean, so I'm not. I don't expect this definition to make perfect sense, like be perfectly clear, like what this kind of means geometrically on first glance. You know, the point is this is some very explicit calculation in the intersection theory that we can do, at least there's like it's a natural notion in the kind of local intersection theory, and so the theorem of Massey is like in the complex world, the dimension of the minus I stalk of k at the point x is less than or equal to the ith polar multiplicity.
And does it define the polar multiplicity like you, or using the conormal using more things related to the conormal.
Sorry, I didn't understand the
It
question.
defines the polar multiplicity exactly like this, or?
The definition he uses is somewhat different, but I think it's equivalent to this. So the other way to define it is to only intersect with a general projective subbundle, and then push forward to y and take the usual multiplicity after doing that, which is clearly equivalent to this. But I think that's closer to the definition that Massey gives. But I mean they're equivalent. Of CCK at x and what I did is the same in characteristic P. So this theorem gives the strategy to bound the dimension of the stock of a perverse sheaf, and it's a strategy which is kind of more straightforwardly kind of algebraic geometric, because in algebraic geometry it's not always clear how to bound things, but we just need to calculate things. We need to calculate the characteristic cycle and then calculate these multiplicities. So there's kind of two parts to what needs to be done. What is the characteristic cycle of these eigensheaf constructed by Drinfeld, and then what is the multiplicity of that cycle? The characteristic cycle of the Haka eigensheaf So this is going to be a cycle in the cotangent bundle of bund 2n, and to just, all right.
Good question. Yeah. Are these? So are you looking at bund 2n as a stack? And
yes.
Is there a well-documented notion of characteristic cycles of perverse sheaves and stacks?
No. So the characteristic cycle of a perverse sheaf on a scheme, it behaves very well under smooth pullback. And since stacks always, or we're working with Artin stacks, which have smooth mapped from schemes, what we can always just do in practice is calculate the characteristic cycle on a scheme with a smooth map to the stack. And that's just what I'm doing. So that is kind of good enough for all practical purposes, unless you want to push forward along a map of stacks, which is not schematic. And then I think there's a genuinely new question. But for everything that in this argument it seems to make sense to do with stacks, you never need to do that, and so you can just use the scheme theory, and it's fine. So we need to, okay, so this lives on the characteristic cycle on the cotangent bundle of bund 2n. Yes, and I kind of want to ignore the fact that bund 2n is a stack and not a scheme here, and it's not clear what the correct definition of the cotangent bundle is. It kind of just seems to work out fine. So we have to understand what is this cotangent bundle so we can describe what the characteristic cycle looks like on it. So first, I'll describe even more simply the characteristic the cotangent bundle of bund 2. So the T star bund 2 has a description as a moduli space of Higgs bundle. So bund 2 is the moduli space of vector bundles. I'll just use a set notation. It's the space of pairs of V of vector bundle on, I guess we're just P1 here, but I mean the same thing works over any curve, and phi a map from V to V tensor, the canonical bundle of P1. So this is the notion of a Higgs bundle. It's a vector bundle with an endomorphism where the endomorphism is twisted by the canonical bundle. And you can see by a very simple Serre duality calculation that this shows you the cotangent bundle of the moduli space of vector bundles. So for Bun2n, it's just a little bit more complicated. We're going to take a point of Bun2n, so V a vector bundle on P1. And then S a sub line bundle over N. And then phi, what happens to phi is that it essentially is allowed poles at the points of N. So it becomes a map only after twisting by N. Whose fiber at the points of N has kernel and image inside S. So the fiber of this endomorphism at a point of N, which you can think of, if you think of it as a poles, you can also say the residue at the pole, is an endomorphism of the fiber. It's basically a matrix. And we're saying that the kernel and image lie in this particular one-dimensional subspace. We're saying it's basically a nilpotent matrix. And it's a nilpotent matrix lying in a particular one-dimensional subspace of the space of matrices. So if
characteristic cycle was usually defined for smooth space. Here the bun is a stack, but also it's not necessarily...
stabilizers.
What?
Yeah.
Yeah, so when I say the characteristic cycle of a stack, what I really mean is I'm just imagining I have a scheme mapping to the stack smoothly, and I'm referring to the characteristic cycle after pulling back to that scheme.
But so you embed the scheme in something smooth to do this.
But I mean, Bun2n is...
It's almost, no, we have trivial bundle, yeah, 0. He gets 6 with the...
I mean, it's smooth, because it's...
Because on the curve, there are no obstructions.
Yes. There are no obstructions to deforming a bundle, so Bun2n is smooth as a stack. And so if you choose a scheme mapping smoothly to it, it'll be smooth as a scheme. But yes, if I were in a singular setting, I would be embedding it into a smooth scheme. But there's no relevant singularities of Bun2n. And then, so what is the characteristic cycle of K? I claim it's just basically the set where phi is nilpotent. And this is a cycle theoretic statement. So you can say that a matrix is nilpotent by setting its trace to 0 and its determinant to 0. The trace will lie in this Kp1 of n, although it can't actually have poles at n, so it'll just lie in the sections of Kp1. Okay, so there's no possible trace. And the determinant will lie in Kp1 squared of n. And so setting the determinant to 0 is giving me a bunch of equations. And I'm taking the characteristic cycle as like the complete intersection of those equations.
So you're saying it doesn't even depend on f, it's just...
Yes, for a cuspidal eigensheaf, it does not depend on my choice of modular form. It only depends, well, for a new form, it only depends on the level. And so this space, the nilpotent cone in the moduli space of Higgs bundles, is a subject that shows up in many areas, in particular in the geometric Langlands program and in other areas where people are looking at these Higgs bundles. It's the 0 fiber of the Hitchin fibration. yeah, I'm really taking the fiber of the Hitchens vibration in a cycle theoretic sense. And so.
And it's really an equal sign, not just a containment.
Yes, it's an equal sign, yeah.
It looks again strange. I mean, maybe my previous question was not. So of course, so we know that the band we said that they are smooth in the sense of stacks. So the cotangent bundle you can take after on a scheme mapping, but then you describe it as something which is itself a stack. But is it smooth? This kind of Higgs. I mean, the cotangent bundle something smooth should be smooth, but then. What you're describing on the right-hand side is it smooth or? It's very.
I think it's local. It can make it smooth by using some level structure, some other points.
Yeah. Yeah, I mean that's roughly what we're doing here.
I mean, it should be smooth just because this is like the correct derived calculation, and then it just lives in degree 0. So it's just a map of vector bundles. I mean,
No, but then the derived thing. It seems that the derived will have also H1. Here you take H0, which is Holmes, and ignore the H1.
you have an H1?
I don't know.
So at some particular points, you will have an H1 at points. If your vector bundle splits into a sum of line bundles. Well, I mean, you sort of always have H1 because you always have scalar Hams, but then you have more Hams if it splits, and then even more Hams if it's unstable, highly unstable. So. Okay, well, let me make a comment on stacky issues is that in Drinfeld's construction, he considers a space like Bun2 prime that maps to Bun2, or Bun2 n prime that maps to Bun2 n, which parameterizes pairs of a vector bundle and a sub-line bundle. And you first construct the eigensheaf up here on Bun2 n prime, and then show it descends to Bun2 n. And Bun2 n prime, because the points have extra structure, they have much fewer automorphisms, and you know, in the relevant places, it's a scheme, and the argument is really proceeding on Bun2 n prime. So in the actual proof, we're studying the characteristic cycle on Bun2 n prime, rather than the characteristic cycle on Bun2 n. I'm talking about it in Bun2 n because this gives like a more elegant geometric picture that I think is good. I think it's the right way to think about it for kind of the general case, like if you think about generalizing to other groups, for example. But the argument somehow doesn't actually directly involve Bun2 n. It really is involving Bun2 n prime, and the actual polar multiplicity calculations that are being done are ultimately being done for like sheaves on projective space in the paper, because this has many components which are isomorphic to a projective space. So there's kind of none of these stacky issues kind of directly appear, but yeah, I mean.
Yeah, I don't understand, because I know that for a stack you can define a tangent space. This is no more way, but the cotangent twist, I mean, I'm not sure, but so this kind of, the right-hand side should be somehow related to the cotangent bundle of the smooth things over the stack, but you didn't describe exactly how it goes. I mean, so it's very informal kind of, I mean, it's not clear what is the meaning of this. But that doesn't assume it makes sense in some sense. But
yeah, can we please do that? we could talk. Yeah, we could perhaps talk later about it exactly.
If I will get some bound for at points which are not stacky points, yeah.
Yes. Well, I mean, technically, every point is a stacky point if you don't ignore the scalar automorphism. But of course, you can get rid of the scalar automorphism. But yeah, so yeah, we can get a bound away from stacky points, and somehow analytically, the stacky points are probably a little bit easier to handle. So that's probably is essentially the main task. Okay, so this kind of this formula, the characteristic cycle should be the nilpotent cone, is at least morally true for eigensheaves in great generality. So Langlands and Drinfeld did in characteristic 0 a construction of Hecke eigen D modules, and this is the fact that it's a nilpotent cone is a theorem in their setting. Yeah, for any group. And so you should believe, it's very reasonable to believe that also for L-adic sheaves in characteristic P, the characteristic cycle is essentially the nilpotent cone in great generality, although it's not clear how easy it is to prove that from the constructions that we have of eigensheaves in characteristic P.
Are the components Lagrangian in this setup, or do you expect it to be true for the Hecke eigensheaves?
So I think they are still Lagrangian in a kind of, yeah, I think they will still be Lagrangian in characteristic P, but some of the sheaves you go through to construct, well, okay, there's the notion of being Lagrangian, and there's the notion of being the conormal bundle of the support. And in characteristic 0, those two things are the same, but in characteristic P, they're not. And I think it might be the case that all the cycles appearing in here are Lagrangian, but it's definitely not the case that all the cycles appearing in the argument are the conormals of their support. There are cases when it won't be a conormal bundle. Maybe not for the eigensheaf itself, but for the like Whittaker sheaf you use to construct the eigensheaf. Yeah, so all of this reasoning reduces you to a problem which now does not involve any automorphic forms of reverse sheaves at all, and just involves intersection theory. We have this cycle, the nilpotent cone, and we want to calculate its polar multiplicities in this sense. And that is something which looks possible to do. You know, I don't see any obstruction to doing it for any group on any curve to calculate, or at least bound, these multiplicities of the nilpotent cone. But I did it only on P1 and only for GL2 and for these square or these new forms. So this is level structure. And the reason I did it is because there's a trick that makes it much easier to calculate in this genus 0 case. So what is the kind of trick? So our Higgs field is given by a 2x2 matrix, which is nilpotent, which is so C is allowed to have a pole. At some point, and is nilpotent. Okay, and so there's a very simple observation about 2x2 matrices where the entries are functions, and A and B and D can't have a pole, but C can have a pole, which is if C has a pole at a given point, then B has a 0. because if A and D don't have a pole, then AD doesn't have a pole. So if AD is equal to BC, because it's nilpotent, if C has a pole, B must have a 0. And in this case, we can conjugate to some matrix like A, T inverse B, T, C, D, with no poles. So what this is saying is if you have one of these endomorphisms which is nilpotent and has a pole, then either it's an ordinary endomorphism with no pole, or after modifying your bundle, it has no poles. And this lifts to the level of cycles. At each of these points where you're allowed a pole, you can split this nilpotent cone as a cycle into two pieces. One is your nilpotent cone not allowing a pole, and the other is the pullback. The nilpotent cone for like a modified vector bundle, not allowing a pole. And so using this, you can write the characteristic cycle entirely in terms of the characteristic cycle with no level. Or if you have the nilpotent cone of Bun 2n in terms of the nilpotent cone of Bun 2. Okay, except now my stacky troubles are very bad because every point, if in genus 0, every point of Bun 2 is a highly stacky point. It's not even a little bit, it's very stacky. So what I really mean by this is if you choose some scheme mapping smoothly to Bun 2n and like look at the nilpotent cone kind of pull back to that, you can write it in terms of the nilpotent cone of some scheme mapping smoothly to Bun 2. And the nilpotent cone of a scheme mapping smoothly to Bun 2 P1 is something that's possible to calculate very explicitly, precisely because all the points are these highly stacky points, like Bun 2. There's a very simple description of each point, and you can make a scheme mapping smoothly to a neighborhood of that point and do the calculations very explicitly there. You can calculate the characteristic cycles or the nilpotent cone for Bun 2. You can calculate the polar multiplicity of the nilpotent cone for Bun 2 and use that to calculate the polar multiplicity of the nilpotent cone for Bun 2n. So the nature of this level structure in GL2 lets me reduce to the case where there's no level structure, and the fact that they're genus 0 makes the calculations very easy to do in the case when there's no level structure. And that gives some explicit formula for the polar multiplicities in terms of the structure of the bundle. And then you can plug that into this Massey formula and get a bound for the function. And then the bound will vary from point to point, and you kind of optimize it. And that gives the theorem. You look at the worst point, and that gives the theorem.
Could I just ask you a question to make myself more comfortable with the passing to the atlas and so on to is it true then that if you have like a smooth map and a perverse sheet on the base and you pull it back in the perverse sense and you choose a point in the fiber, then the polar multiplicity there is the same as the polar multiplicity there, or? Yes,
that's true. Yeah. So the polar multiplicities are preserved by smooth maps, exactly. And so that follows from a statement of the preservation of the cotangent of the characteristic cycle under smooth pullbacks, and then an intersection theoretic calculation. Yeah. So the.
Okay. Using this second description of push forward from the projected bias cotangent. Yeah. Okay. Yeah. Does that make sense? Oh yeah, it does make sense. Yeah. Okay.
You have noticed another reduction. You've noticed another reduction in the higher rank case with the extent of GLN. There's no trick.
Yeah, I don't think so, right? Because you have, if I have a bundle, like if it's a new form, you would, like in GL3, you would have the poles are allowed to be here and here. And if there's poles here and it's nilpotent, like what is it forced to be 0? Like it doesn't.
So consider the geometry of this. I don't know if this suggestion makes sense, but suppose you have a smooth scheme mapping to bound to this. So then you have also a groupoid. So you can think of the orbits. So somehow this should describe the cotangent boundary of this smooth scheme upstairs, but only the part which vanishes on the orbits, on those subvarieties which map to the same point down. I mean, it seems that this should be the interpretation of this formula that you are calculating.
Yeah, like
which is 0 on some submanifolds, which.
Yeah. So you have a smooth thing. Yeah. So you have a smooth thing mapping to your stack, and you're only interested in the piece of the cotangent bundle which consists of vectors which are transverse to the tangent space of the fiber. And your cycle will be a cycle in the cotangent bundle of that pullback scheme, but is supported on that subset, that sub.
Yeah, and then this would be roughly the, okay.
And that, like, if you look, there's, if you look at Bun 2P1, how do I make a smooth scheme mapping to this? I mean, a very simple thing I can do is I can take a line bundle O of A and a line bundle O of B, and there's this vector space parameterizing extensions of O of A by O of B, and there's a universal family of vector bundles over that vector space, and I get a map from that vector space to Bun 2, and that map is smooth in the P1 case for any, well, whenever the extensions are kind of non-trivial, so whenever A is greater than or equal to B or less than or equal to B, whichever one that is. And so those vector spaces are schemes mapping smoothly to Bun 2, and you can look in, there's an equivalence relation on the vector space, and you're looking at exactly the piece of the cotangent bundle which is transverse to that, which is some kind of complicated nonlinear thing. It's not obvious what it is, but it's also not very hard to write it down in terms of polynomials in one variable. And then because in this Bun 2 case, I mean, in fact, every phi is nilpotent. Like, it's not possible for phi not to be nilpotent on P1 because of the negativity of this KP1. Everything is nilpotent, but the nilpotent cone is really giving you just a cycle structure on that kind of closed subset. And it kind of, but it works out to be some very explicit geometry with polynomials, and then it's compatible. There's some compatibility with the Bun 2n characteristic cycle.
Isn't it possible, maybe this is what you meant, but like take a scheme which of course you have some control over mapping to the stack, and what you really care about is the stocks of the perverse sheaves on the stack. So you pull back the perverse sheaf to the scheme, but there you do Massey's formula, and then you sort of use some push down formula for, is that what you, I mean, in some sense you're never really on the stack.
Yeah, so there's no actual stacks in the paper. Well, in fact, because I'm working, in fact, I work with schemes that are mapping non-smoothly to the stack, and you calculate the characteristic cycle really up here, and then, well, it may or may not be smooth. So it might not be smooth. And so in the case that it's smooth, that allows you to calculate the characteristic cycle down here, but it's actually kind of the non-smooth case where you get a slightly better bound. But yeah, that's the point. Because we only care about the stalks, and we're not doing something like taking the cohomology of the stack with coefficients in this sheaf, we don't really have, we can do everything after pulling back to a scheme, and that's really where I'm doing the calculations. But yeah, I think talking about it in the abstract setting is helpful. Okay, if there's not more questions about that, I'm going to switch to a completely different topic. Okay, I'm going to begin with a topic which is almost entirely unrelated. I'm going to talk about Cohen-Lenstra theory. So Cohen and Lenstra were studying for K let's say an imaginary quadratic field. The class group of K, which parameterizes ideal classes of K, although it was originally defined by Gauss as parameterizing certain equivalence classes of binary quadratic forms, is a finite abelian group. And the one thing that we know about finite abelian groups, or I don't know the one thing, but one thing we know about finite abelian groups is they split into P groups for product of P groups for each prime P. A product over P of some P part, class group of K, P infinity torsion. And it's very natural to study it one prime P at a time to look at the P group, the P part. And if you look at the P part of class groups, for example, if you look at them numerically, it seems to behave very randomly. You can look at you can put all the quadratic fields in order by discriminant. There seems to be no relationship between the P part of the class group of one field and the next field. Or you could look at them maybe by L-adic congruence mod L for the discriminant. There's no relation between the class group, the P part of the class group, and the P part of the class group of another field, discriminant congruent mod L or congruent mod P, except if P is 2, it behaves in a way that's somewhat non-random. But in general, it seems to behave very randomly. At any time, in number theory, something that seems to be random, or I guess in mathematics, you want to know what is the probability distribution. What kind of random process does it behave like? And so let me formulate it vaguely and then formulate it precisely. What is the probability that the class group of K is isomorphic to G for G a fixed finite abelian P group? Oh, yes, class group A, P part.
For given P, it's typically has P element of seldom P squared, some P cube.
Yeah, well, I'll write a formula and then we'll talk about the meaning of the formula. But yeah, it's usually pretty small, the P part.
It's equal to, I think you can calculate either the mod 2 or the part killed by 2. I mean, something you can calculate always using the number of varieties.
Exactly. Yes. I want to avoid that, so I'm going to hopefully remember to write P odd, because for P2 the behavior is different. So the original conjecture of Cohen-Lenstra, we're going to take P odd and G a finite abelian P group. And we're going to take, so number theory always consider probabilities in the limit as some parameter goes to infinity. And we're going to look at the average over the set of k over q, an imaginary quadratic field of discriminant less than x. So we're going to average over this set by dividing by the size of the set. And in the numerator, we're going to put the set of all such k whose class group is isomorphic to G. So k over q, imaginary quadratic, discriminant of k less than x, class group of k, p to the infinity part is isomorphic to G, should equal 1 divided by the order of the automorphism group of G times product j equals 1 to infinity, 1 minus p to the minus j. So this ratio, the proportion of imaginary quadratic fields with small discriminant, where the class group is isomorphic to G, should converge as x goes to infinity to a limiting value. The limiting value is proportional to the inverse of the number of automorphisms of G by some constant proportionality, which is exactly the constant that's needed to ensure that these terms sum to 1 over all finite abelian p groups. So for p large, this constant is pretty close to 1. And so most groups have the p part of the class group trivial. And if it's not trivial, then it's probably the group that had the smallest number of automorphisms, which is like the cyclic group Z mod p. And next most likely would be the cyclic group Z mod p squared. And the product Z mod p squared is a little bit less likely than Z mod p cubed. You can kind of, so it's usually pretty small, and even when it's not small, it's usually cyclic, because cyclic groups have fewer automorphisms than the elementary abelian p groups. So this is the distribution, and it is supported by a lot of numerical evidence, and we now also have some theoretical evidence. We have a conceptual understanding of why this is true.
Where is it important that k is imaginary, quadratic, or complex? Is this?
So are you asking about the difference with real quadratics? So for real quadratics, Cohen and Lenstra also made a formula. And it's just slightly different. So the real quadratic formula, everything is the same, and then you have 1 over the order of G times the order of the automorphism of G times the product j equals 1 to infinity, 1 minus p to the minus j minus 1. So for real quadratic things, the larger groups are even less likely than they are in the imaginary quadratic case, which makes sense, as you can see from the class number formula. The class group is smaller in the real quadratic case than the imaginary quadratic case because of the presence of the regulator in this formula. So if the class group on average is smaller, then probably it makes sense that p parts are smaller too.
And do they have some heuristic justification?
Yes. So the original heuristic justification of Cohen and Lenstra, I feel like is kind of weird. I feel like we now have a better heuristic justification, which I will talk about. I mean, in short, my primary heuristic justification of this is that it's true or almost proven to be true in the function field case, thanks to the work of Ellenberg, Venkatesh, and Westerland. So, I mean, the simplest justification you could give is you could say that if you have a category, it's natural to measure each element of the category by the inverse of the order of the automorphisms. And so that makes you think that a uniformly random element of the category should be choosing each element proportional to the inverse of the order of the automorphism group. and that would be given by this distribution. But why imaginary quadratic field class groups should be uniformly random P groups kind of needs an additional justification, and I think the function field model is the clearest model for that. Okay, so for higher rank, okay, so the question of what happens in higher rank is exactly the natural justification, the natural generalization people looked at next. So I think Cohen and Lenstra did something for abelian groups, but the really kind of generalization is due to Cohen and Martin. Well, let me say something about the status of this conjecture. It's still, no one has any idea how to prove this. But in number theory, often when we have a conjecture we don't know how to prove, that doesn't stop us from trying to come up with a much more general conjecture that includes it as a special case. And so I want to mention kind of two different directions you can go in to generalize this conjecture. So one is Cohen and Martin. And so they considered exactly generalizing from quadratic fields to fields of higher rank. And if you think about that, it immediately becomes clear the Galois group of the field is very important for understanding the behavior of the class group. And so it's natural to consider Galois fields of a given Galois group. And if you're considering Galois extensions, you might as well not just consider Galois extensions of Q, but Galois extensions of another base field. So they gave a conjecture for class group of K, maybe mod class group of F, P infinity part, where K is a random extension of a fixed field F with Galois group gamma. And let's take P not dividing the order of gamma for the same reason that P2 is bad for the original class group.
Should we take care about real, imaginary, and infinite?
Oh yeah, and then we would say fixed. I think you can do a fixed type at infinity. Fixed type at infinity. So for every real place of F, you would fix an element of order 1 or 2, or a conjugate class of order 1 or 2 in gamma, and the complex conjugation at that place should behave like this. So in this setting, the class group it requires an action of gamma. So you can think of it as a module for ZP adjoint gamma, and they predicted it a probability distribution over modules in ZP adjoint gamma, which is a natural thing to do in this setting. And so they made a conjecture in this great level of generality, which was a great thing to do, but unfortunately, it is not correct. So this is so this was noticed first with numerical evidence by Mala in the case where F contains the p-th roots of unity. So it's never correct if p is 2, because we always have the second root of unity in our number field. And then for other larger primes, it can fail if you are starting from the wrong field. And so okay, so since then, people have been working to give a corrected conjecture in the case where there's roots of unity. And so this is something that a lot of people have worked on in special cases. And then recently, Melanie Wood and I gave a conjecture in the same level of generality as Cohen and Martinet, but we believe fixing the issue with the roots of unity. So we gave an amended conjecture handling roots of unity appropriately. But I don't want to talk about that directly. I want to put it in a kind of context, which is to do with thinking about a different generalization of the original work of Cohen and Lenstra. Which has to do with, well, one of the main reasons class groups are of interest in number theory is class field theory, which tells you that the class group of K is the Galois group of the maximal abelian unramified extension of K. And so it's very natural to try to generalize this by just deleting the word abelian. Consider the Galois group of the maximal unramified extension of K. You can think of it as the fundamental group of the scheme OK. So the question is, what is the distribution of the Galois group of the maximal unramified extension? No. If you want. Well, so basically, what was done in practice is you can fix S any set of primes, and then maybe work with an S extension. So an extension where all finite sub-extensions have, or like a Galois extension where all finite Galois extension are divisible only by primes in S. And so the easiest thing to do is to do a single prime P. And that's what the first work in this subject did. In particular, I think Boston, Bush, and then Hajir did the case where S consists of a single prime P. Yuan Liu, Melanie Wood, and David Zurich Brown did a significant generalization of this, where S consists of all primes, or roughly speaking, they only did it for the Q of the base field, but if you kind of apply the same method for general F, it consists of all primes not dividing the order of gamma, the number of roots of unity in F, and then also maybe you get worried about the fundamental group of F, so the Galois group of the maximal and ramified extension of F.
Sorry, what was gamma in this case?
I guess so gamma should be the same thing it is over here. We're going to consider K a gamma extension of a base field F. Yeah, gamma will be finite, yeah.
But the maximal unramified extension is not finite. I mean, I think sometimes it's not finite because...
Exactly, the maximal unramified extension is often not finite.
But if you fix a prime, then no, even though...
If you fix a prime, it is still often not finite. Okay. So even if you fix a single prime, there are examples showing that it's the maximal P extension is infinite. And so, yeah, so what I mean by distribution is a little bit unclear because the set of possibilities is, operator an uncountable set. So I need to choose a sigma algebra on it for the distribution to make sense.
Unramified includes the condition at the real place that is needed to get the you have the strict class group which corresponds to another notion
of. This work is everything is split at infinity. It's possible to consider the problem not split at infinity. Let me say what we're trying to do, and then let me say. So the primary goal of my joint work with Melanie is to simultaneously do the non-abelian generalization and handle the roots of unity. So we want to take this previously existing result and which in the non-abelian case and remove the restriction coming from the roots of unity. And then as kind of a test case kind of thing, first step, one of the things we did is we did the abelian case, removing the roots of unity restriction. Let me say what I mean by distribution in this context. So the set I want to work with is the set of isomorphism classes of profinite groups, or I should say small profinite groups, where small means only finitely many open subgroups of index n for all n. And then with a topology and a sigma algebra generated by the set of profinite group X such that G is a quotient of X for a finite group G and their complements. So this topology basically reflects that I want to distinguish two profinite groups from looking at them only via finite groups, so only via their finite quotients. And so a natural set to consider is the set of all profinite groups which have a given finite group as a quotient, or a set of all profinite groups which don't have a given finite group as a quotient.
Is topology house rule?
Yes, it is. yeah, which is not not super easy to see, but I think follows from some calculations.
Okay, yes. Yeah, essentially you have to prove that if the same groups are quotients, then the groups are isomorphic. So somehow you try to, well, I think it should follow some compactness argument.
Yeah.
You try to take a quotient of one, then you get a quotient of the other, which is the same. Then you take a bigger quotient of this side and go back to that side. Then you can go back and forth, take the limit in some sense. I think so.
Yes. The way the thing to do it is a little bit more complicated than that. I'm not 100% sure that way works. So there's certain canonical finite quotients of a profinite group you can define. For example, the maximal quotient that's a finite abelian P group, and there's a family of canonical quotients, and you can try to match up the canonical quotients of the two groups to each other. And I think it's a little bit easier to do it that way, but probably both ways work. So this is an actual topology. There's a couple different ways to describe this topology that get the same answer. And we're describing the distribution as a measure on this space. Or maybe we do the same thing for groups with an action of gamma, and then we do the topology for groups with an action of gamma, and then we describe it as a measure on that space. So that's our goal. It's currently a work in progress. So what I want to explain first, because of the theme of this series of lectures, is how does this connect to geometry? So in the function field setting, if I have an extension of fields k over f with Galois group gamma, then this corresponds to a covering of curves that is a finite covering with Galois group gamma. And then the Galois group of the maximal unramified extension of K is essentially the fundamental group, the étale fundamental group of the curve D, because unramified extensions correspond to étale covers of curves. So the question is, what is the distribution of pi1 of D for random covers D? Sort of a function field analog. We're actually looking at something slightly different. So as I mentioned briefly, you want the number field thing to be split at infinity. And so you do the same thing. In the function field case, you want to work with covers that are split at infinity. So you mod out by some Frobenius element at infinity. But for what I'm going to explain, that's not an important detail. So, and if you think about this question geometrically, you rapidly run into the trouble that the fundamental group on itself is not a particularly concrete geometric object, the étale fundamental group. So the fundamental group is defined so that actions of the fundamental group on finite sets classify finite tile coverings. And it's really the finite tile coverings that are nice geometric objects we can understand rather than the fundamental group itself. So let me give it a precise statement. So pi1d is defined so that surjections from pi1 of d to g are the same thing as finite étale Galois covers with Galois group G. And these covers are FQ points. Yeah, connected. Of a moduli space. So there's a moduli space of, well, first you take a cover D of your base curve C with Galois group gamma, and then you take some covering of that with Galois group G that's connected. That gives you, a covering of C. And this is some geometric object, so it lives in some moduli space. So the thing we know how to do, I mean, in some sense the only thing we know how to do when applying geometry to number theory is to count FQ points on these spaces.
Yeah, but gamma is very ramified, yeah?
Yeah, gamma, this one is ramified and this one's unramified, yeah. So what does counting points on this space do? Tells us the average number of surjections from the fundamental group of D to G over covers D. So we have a space, a Hurwitz space parameterizing basic covers of the base curve with a given Galois group, which we can factor into maybe an extension of gamma by G with particular branching type. And by counting points on this space, we can calculate the average number of surjections onto a fixed group G. And so
actually, surjections you can forget by inclusion exclusion principle.
You can calculate homomorphisms, exactly. So surjections and homomorphisms give the same information. So the reason that I'm considering surjections and not homomorphisms is I haven't written down any formulas, but if you look at the formulas for surjections, they're much nicer than the formulas for homomorphisms in this setting. So the expectations you get make much more sense if you express them in terms of surjections. And so it makes sense to do all the calculations on the level of surjections rather than homomorphisms.
Can I ask a question with that? Coming back to the original.
Yeah.
So like you can obviously get rid of the odd G factor if you like parameterize isomorphisms instead of. So what happens if you then take surjections?
You just get rid of everything. You just have one.
Okay, yeah.
And then here you get rid of the ought and this, and you just have 1 over G.
Okay, yeah.
So they really are very nice formulas when you count surjections. Yeah. And then so what happens if you count homomorphisms? You would hear the homomorphism version of this is just the number of subgroups of G. And here it's the sum over subgroups of G of the inverse of the order. So like it's very clear that you get a nicer formula if you count surjections rather than homomorphisms. So the key key question is if we have a measure on the set of profinite groups, is mu determined by like the integral of the number of surjections from x to g d mu of x, like the integral against this measure of the number of surjections. If this measure is determined by the expected number of surjections, then if we calculate the expected number of surjections, we've calculated the measure. So modulo, there's a difficulty. You might worry about a sequence of measures where the limit of the measures, the moments of the limit of the measures, or the expectation of the limit of the measures, is not the limit of the expectations. But it turns out that the same tools you need to answer this question are closely related to the tools you need to answer that like.
Because it's not bounded. If you have space of the number of surjections is not bounded, you only know it's finite. So you don't know the integral is finite. Maybe this is what you're.
Yeah, that's a related question. Yeah. So so this is an analog of a very classical question in probability theory. If you have a distribution on the real line, is it determined by its moments, which are the integrals of powers of the real variable against the measure? And the answer is it is uniquely determined by the moments, as long as the moments don't grow too quickly in some precise sense. And a similar statement will be true here.
But in practice, aren't all your profinite groups like finitely generated as profinite groups?
No, but total convergence.
Probably, but why do you think that helps?
Well,
No, but when you consider this covariance, the number of generations will be very big.
But is it bounded? Are you working? Is it so? When you are doing this probability distribution, your spaces are such that do you have some uniform bound over the space?
There's no uniformity of the bound. No. So the only thing that's involved, the only bound involved in the probability is the smallness criterion, which just said that there's finitely many open subgroups of a given degree. So much weaker than finite generation.
Like in topology, if you consider cover compared some very many points, but in a very small degree, then the genus will go linearly, then we have kind of number of generators will grow by size of this.
Yeah, so the number of generators, the potential number of generators is growing rapidly. So yeah, we don't want to do it that way. And so this kind of question is a question that had recurred multiple times in Cohen-Lenstra theory. So notably, in the work of Ellenberg, Venkatesh, and Westerlund proving a function field analog of this statement, they did it by calculating certain moments. They did it by counting points on some of these Hurwitz spaces. And so they needed to check that the measure, this Cohen-Lenstra measure, was uniquely determined by its moments. And in that paper, it wasn't very hard to check. Like, it's a very short proof that this measure is determined by its moments. But in subsequent work on the problem, in every new setting, people need to determine a new measure was determined by its moments. So maybe you consider a Abelian group with extra structure coming from the root of unity. Or you consider profinite groups, or maybe you want to consider profinite group with some extra structure. Every time you needed a new measures from moments theorem to answer this question on a different set, which it got more difficult over time. And so this obviously is not a good situation. And so what Melanie and I set out to do, so what was it, a theorem of Melanie Wood and myself gives an answer not just for profinite groups, but for pro-objects of many other categories. So we consider a category of objects, categories satisfying some hypotheses. We'll define a set of like pro-objects in that category of isomorphism classes with like a topology like this, and we'll think about measures on that set. We can define a notion of moments for measures on that set using surjections onto finite objects, and we'll give a criterion for when a measure is uniquely determined by its moments. But we did a little more than that. We also answer existence questions, and we construct the measure. So you might not just want to know that there is only one measure with those moments. You might want to know when does a measure with those moments exist. And we also give an answer to that question. And what's more, we can give a formula. We give a construction for the measure, meaning we give a formula for the measure assigned to the open sets in a particular basis. And then the reason that's kind of important is here you have kind of nice formulas for the probabilities, but as people tried to generalize those results in different directions, getting nice formulas for the probabilities got harder and harder. And the other thing you could try to do other than a nice formula is like a random model, getting define a notion of a random group using maybe random matrices of a particular type that predicts the distribution. But doing that also got harder and harder. So you would have to guess the distribution before proving that it's correct, which was difficult, but also conceptually unsatisfying. And so what we want to do is just calculate these expected number of surjections and then plug it into some machine and have the machine spit out for us a formula for the measure, which seems like a much nicer thing to do in general rather than to have to guess the measure every time. So let me talk more about the details of that. What kinds of categories does it work for? What the structure of our criterion is, and what we're capable of doing with it. Let me talk more about that next time because we're out of time today.
So you don't just construct like one measure on like for these like spaces of like isomorphism classes and categories, but rather you construct like basically you say, well, give me a list of moments. If it satisfies something, then you can construct it.
Exactly, yeah.
So like, is there some kind of canonical choice of like moments or something, or is it like each problem you get like?
So one thing it depends on what you're doing. If you're doing number theory, you just have to figure out what the moments are in your given like number theoretic problem, and it depends. The moments depend on things like if you have an imaginary quadratic field or a real quadratic field. But there's a very natural choice to consider for a wide variety of problems, which is set all the moments to be 1. So one thing we did is we played around with a few different categories and saw what happens when you set all the moments to be 1. And then often that does turn out to be what comes out of some some natural model, like some random matrix model. But there's like lots of other natural things you could try setting the moments to other than 1 that you can apply our methods to. more questions?
And so next time you're basically going to explain like what's going to happen if you apply this kind of like basically how do you compute the moments, say in some kind of finite field situation.
I'll maybe say a little bit about that. So let me say something about, well, we're not actually able to compute the moments that well. So in most cases, we can only compute the finite field moments in the Q to infinity limit. But I will say something about how we compute the moments in the Q to infinity limit. And then I'll say a little bit more about this theorem and a little bit more about the applications of this theorem.
Can I ask, there's this weirdness about roots of unity causing trouble, which I don't understand. Is it more evident in the function field case? Why, like, is it something, I mean, is it like ground field extent? I mean, well, there's no, or is there no analog, or what's?
Yeah, no, there is, so, yeah, so the way it comes up is, well, let me say it like this. So the dominant term in counting points on this moduli space is understanding the connected components, and in particular which connected components are defined over the base field FQ. And so how can you get an invariant that separates the components here? One way is to find some universal cohomology class and integrate it over the curve. And so what does that integration involve in the finite field setting? It involves Poincare duality in italic cohomology, which has a twist by the cyclotomic character in it, a twist by the roots of unity. And so what that tells you is, in the case when you don't have very many roots of unity, when the base field is small, the integrals of a lot of cohomology classes, like in the group cohomology of this, have to be 0. And so the only one component is defined over the base finite field. But if the base finite field contains more roots of unity, then the integrals are not forced to be 0, and multiple components are defined over the base finite field, which makes the moment larger. Maybe I'll mention, one thing we studied using our methods is a kind of topological analog, where you look at the fundamental groups of random 3 manifolds. And in that topological analog setting, it behaves most like the limit of this number field thing when you have all the roots of unity. You add as many roots of unity as you can. So in that sense, like, you can say maybe roots of unity aren't bad in causing problems. They're good in making the situation more like topology. They're making the field more oriented. It's kind of what they're doing.
But the Brouwer group never plays a role, or it never messes anything up.
Yeah, I don't think so. So
because it's like, okay, you have roots of unity, you have maybe something like torsion and pick. I mean, it's not clear. Well,
yeah, I mean, it's all related. So the way that is clearest for me to think about it right now is that the well, is it kind of, yeah, I mean, you have, so because this G is like group cohomology classes in G map to cohomology classes of your field or of your curve or something like that. Cohomology class is untwisted by the roots of unity. And so the description of like H2 and H3 of like Z mod n, your curve of coefficient Z mod n, is going to depend on where the roots of unity are. And so I mean, I guess the H2, you can connect that. You can connect it up to the Brouwer group. I mean, all of the arithmetic duality ultimately kind of comes from the Brouwer group. But you can phrase it in different ways, and some will involve the Brouwer group. Some will not involve the Brouwer group directly, and some probably will.
So where are the higher, so like the H1 is a surjection or it's related to the coupling, but where do the higher cohomology come?
I'm saying if you have such a surjection, then a cohomology class in G can be pulled back to a cohomology class of D, a group cohomology.
Okay.
Yeah, and that's how cohomology enters the picture. Okay.
And can you say originally what was the heuristic that the real quadratic fields would have a different distribution for? What was the idea?
I think they might have been more motivated by like numerical evidence than by the heuristics. Like if you just look, you generate a bunch of real calculus class groups, you can see that it's not following the same distribution. So the only conceptual heuristic I know. So you can get these distributions out of random matrices. So this is the co-kernel of a random n by n matrix over the p-adic numbers. This is a co-kernel of an n by n plus 1 matrix over the p-adic numbers. And so at some point, people realized that you can actually express the class group as the co-kernel of a matrix if you consider the you choose a large fixed finite set of primes, and you look at the class group. You look at all the divisor classes, all the ideal classes generated by those ideals is like z to the n, and there's a subgroup, and you can check the rank of the subgroup is matching the rank that gives you these random matrices.
So you can also see how the roots of unity kind of appear because they certainly make the groups not free. Make the group of, because if you have roots of unity, you get non-free.
That's true, although it's weirdly kind of not the most important thing. Roots of unity give you some kind of duality structure on the class group. So there's dualities on the class group when the functional case come from the V parent that you can only see when there's roots of unity. Those dualities kind of have a more significant influence on the distribution, I would say, than the torsion part of it.
So you said you looked at the distribution for like something like random free manifolds. Have you also gone through? Have you also been able to prove results in other cases?
You mean like in topology? Yeah. No, we have not looked at any topological model other than random free manifolds. You mean like knots?
Like algebraic curves.
Well, that would be, I mean, it's not obvious what measure you would put on algebraic curves for the complex numbers. But yeah, so we haven't looked at any other cases. If you come up with another case, then the answer will either be, either like you can probably do something with our methods, or it seems very hard to do with our methods, or I don't think the question makes sense. But we haven't done any other kind of topological theorems than that one.